Alright, so this is the chemistry lesson video for chapter 19, section 1. And so we are going to jump into acids and bases and salts, which salts are just compounds that are formed through a neutralization reaction of an acid or base. It's not necessarily sodium chloride. So in section 1, we're mainly going to kind of define what acids and bases are. Now I know you're probably thinking, well, my gosh, why does that take a whole section? It's because we're going to talk about 3 different definitions for acids and 3 different definitions for bases. And it just kind of depends on what reaction you're doing or what application you're using them in as to which definition kind of makes more sense to utilize at that point in time. So acids have a sour taste, change the color of an indicator, can be strong or weak electrolytes in aqueous solutions, and react with metals. So acids. Lemons and a lot of other fruits have citric acid. That's what makes them taste sour. Sour Patch Kids, same thing. If you look at the ingredients, a lot of times they have citric acid in them, and that gives them the sour taste. A gross example of sour tasting acid is when you throw up, the reason it tastes sour is the hydrochloric acid in your stomach. They change the colors of an indicator, can be strong or weak electrolytes, which means they can either fully break up and conduct electricity well, or if they're weak, they partially break up and conduct electricity okay. And then they react with metals. So here's an example of some magnesium metal in an acid, and you can see all the bubbling that occurs. Eventually the magnesium will completely dissolve. And this would be a very concentrated version of an acid. So bases, on the other hand, taste bitter. They change the color of an acid-base indicator. They can be strong or weak electrolytes in aqueous solution. And another thing is they feel slippery. Okay, so bases we don't eat as often as we eat acids, but if you've ever had unsweetened chocolate, I'm not talking about dark chocolate, I'm talking about like unsweetened chocolate. If you're actually in my class, I will bring some and you can taste it. However, if you're not in my class or we're still learning remotely, then you can feel free to get some at the store and try it. When you taste it, it feels like, I don't know, the best thing I can say is it's like there's like chalk in your mouth. I don't know, bitter is just, it's really hard to describe unless you've tasted it. But you'll taste it, it's gonna be bitter. So that's an example of what bitter is. A lot of bases are in our cleaning products. So like if you've ever felt bleach or like Windex or 409, they all feel really slippery, not just like water. That's because they have bases in them. Now, it changes the color of an acid-base indicator, but obviously it would change it a different color than the acid does. So here's an example of a universal indicator. So our acids tend to be the warm colors, and our bases tend to be the cooler colors of the rainbow. They can also be strong or weak electrolytes, which means they can fully or partially break up. And like I said, they tend to feel slippery too. So let's look at some definitions. The first definitions we're going to focus on are the Arrhenius definitions. So an Arrhenius acid is a compound that produces H+ ions, or H3O+, in a solution. Alright, so the reason that I say H+ or H3O+, which is just a hydronium ion, we'll talk about that in a second, is when the acid produces the H+ ions, they're attracted to water, which of course is H2O. So it will form this ion, which is called the hydronium ion. It's just H3O+ because it has an H positive that's been added to it. Depending on what reaction you're looking at, sometimes we'll just write it as H+, sometimes we'll write it as H3O+. It just depends on, do we care that the water is there or not. So a monoprotic acid produces 1 H+ ion. So an example would be HCl. It can produce 1 hydrogen. A diprotic produces 2, so H2SO4. And a triprotic produces 3, so like H3PO4. All right, and so here's an example where they took the HCl, and when they removed one of the hydrogens, they gave it to the water to make the H3O+. And then you're just left with Cl. Alright, so that's the Arrhenius definition of an acid. It produces H+ ions in solution, or hydronium ions. Arrhenius bases, on the other hand, are compounds that produce hydroxide, or OH- ions in solution. So for example, NaCl, that's not even a Cl. NaOH, it produces Na positive and OH negative when it dissolves in water. So an Arrhenius base produces OH-. So now let's move on to a different definition. So Arrhenius acids produce hydrogen ions, Arrhenius bases produce hydroxide ions. Bronsted-Lowry acids and bases, instead of focusing on which particle they produce when they're introduced to water, they focus on what happens to the H plus ion. So H plus ions are also a proton, because remember, hydrogen only has one electron, so if it's H positive, it's lost that electron. Most of them have no neutrons, so it's just one proton. So Bronsted-Lowry acids are proton or H plus donors. So here's an example that I just showed you on the previous slide. So HCl is going to donate its hydrogen to water. So water becomes H3O, and HCl just becomes Cl. So it's an H plus or proton donor. A Bronsted-Lowry base is a proton or H plus acceptor. So here's a different reaction where we have NH3 in water. Well, when you put NH3, which is just ammonia, in water, water gives a hydrogen to ammonia. So see how it was NH3, now it became NH4, and water is down to being OH negative. So see, it's still producing the hydroxide like in the Arrhenius definition, but it is accepting the proton from water. So to figure out the donor and acceptor, you just need to look at the reaction, what's happening in the reaction. So that brings us to the product side of the reaction. A conjugate acid is a particle formed when a base gains a hydrogen, or it's an acid created from a base. A conjugate base is the particle formed when an acid loses a hydrogen, or it's a base created from an acid. So when you get to the product side of the reaction, you have what are formed that are called conjugates. All right, so here is a reaction that we've already looked at, and then notice it has a double arrow. That means the reaction can go in both directions and eventually will reach equilibrium. So we know that HCl is going to donate its hydrogen to water, so water will become the hydronium ion, which is H3O+, and HCl will just be left as Cl. So since HCl is the donor, it is acting as the acid. Since H2O is accepting it, it is acting as the base. Now hopefully right now you're thinking, wait a minute, I thought water was neutral. I hope you're thinking that, because that's correct. Water is neutral, but in specific reactions, it can act as an acid or as a base. Okay, so in this case, it's accepting the hydrogen from HCl, so it is acting as a base. But remember, the reaction can go in the opposite direction too. So once H3O positive and Cl negative form, they can react and make the original reactants. So what's happening on this side? Well, H3O plus, to go back this way, would have to give its hydrogen back to Cl negative. So then H3O plus becomes H2O again, and Cl becomes HCl. So since H3O plus is the donor this time, it is the conjugate acid, because remember, the conjugate was formed. So that means it has to be on the product side. And then the Cl negative is accepting this time, so it is the conjugate base. All right, the other thing to remember is, notice what I put in parentheses here. This is just kind of like a quick way to think of it. So a conjugate acid, so this is our conjugate acid, is an acid created from a base. So if you look, water was a base, and it became the conjugate acid. And then same thing here, a conjugate base, which is our Cl minus, is a base created from an acid. So it was HCl, which was an acid, and it became the conjugate base. And then just don't forget, H3O plus is just that hydronium ion. So let's look at a couple of other examples. So it says a substance that is amphoteric can act as an acid or a base. So an example that I have shown you right here is water. So here's the example we just looked at, where the acid was donating a hydrogen to the water, so it became H3O. So since water was accepting, it's considered the base. But here's an example that I showed you in an earlier slide, where NH3 in water, water gives a hydrogen to the NH3 to make it become NH4. So in this case, water is acting as an acid. Now remember, water just by itself is neutral. Okay, but in certain scenarios, it can act as an acid or a base. It just depends on what's happening with the hydrogens. All right, and then the last definition that we focus on is Lewis acids and bases. So in this example, instead of focusing on what happens to the H positive, we focus on what happens to an electron pair. So see, each one is just focusing on something different. So Lewis acids are electron pair acceptors, and Lewis bases are electron pair donors. Now I know you're probably thinking, how am I going to keep all this straight? Well, Lewis is the exact opposite of Bronsted-Lowry. So a Bronsted-Lowry acid is a proton donor. Well, what's the opposite of a proton? An electron pair. What's the opposite of a donor? An acceptor. So you just take it and reverse both of them. And so then a Lewis base is an electron pair donor. Well, a Bronsted-Lowry base is a proton acceptor. What's the opposite of proton? Electron pair. What's the opposite of acceptor? Donor. Okay, so you can maybe do that and that'll help a little bit. So like in this case, we have these two molecules that are going to bond together. And so if you look, remember, we all know a bond is just a pair of electrons. So if you look, who has the valence electrons to make this bond? Because boron doesn't have any more valence electrons to make the bond. So that means nitrogen is going to make the bond from its electrons. So nitrogen is the electron pair donor, making that the base. And boron is going to accept those electrons to form the bond, making that the acid. All right, and so that's all you have to do is just keep up with who said what. So what are the properties of acids and bases? I'm going to go through them quickly because they're already in your notes. So acids, they taste sour, they change the color of acid-base indicators, they react with metals, and they can be strong or weak electrolytes. And bases, they are bitter, they feel slippery, they can change the color of indicators, and they also can be strong or weak electrolytes. So number 2, how did Arrhenius define an acid and a base? Well, Arrhenius said acids produce H+ ions in solution, bases produce OH- ions in solution. Number 3, how are acids and bases defined by Bronsted-Lowry theory? In Bronsted-Lowry, an acid is a proton donor, and a base is a proton acceptor. All right, so an acid is a proton donor, or H+ donor. A base is a proton or H+ acceptor. And then what is the Lewis theory of acids and bases? Well, in Lewis theory, an acid is an electron pair acceptor. Remember, it's the opposite of Bronsted-Lowry. An electron pair acceptor. And a base is an electron pair donor. All right, so number 5, it says identify the following acids as monoprotic, diprotic, or triprotic. We have H2CO3, so there are 2 hydrogens, so that would be diprotic. For part B, we have H3PO4, so that would be triprotic. Another example, we have HCl, that would be monoprotic because we just have 1 hydrogen. And for part D, we have H2SO4, so that would be diprotic. And one rule of thumb is a lot of times, not all the time, especially if you go into organic chemistry, a lot of the acidic hydrogens will actually be listed at the end of the formula. But if you see something like this, HC2H3O2, this is acetic acid. Notice how we have 1 hydrogen listed in the front and then the other 3 are listed in the polyatomic ion. This is actually only a monoprotic acid because the polyatomic ion is not going to break up. Okay, so in this class, I will make sure to list any acidic hydrogens in the front, but just know that if you move on to other chemistry classes, eventually you're going to get to where you might have like a COOH at the end, and that last H is an acidic hydrogen. But your teacher will cover that for you in those classes. All right, so hopefully so far acids and bases have been pretty easy. So far it's just about keeping those definitions straight.